We want to find out the electric field from a continuous charge distribution. So suppose I have a rod that is length L long and has a total charge big Q distributed uniformly over the entire surface. Okay, so no matter what piece I would cut out, it would have the same density of charge, same amount of charge per size of a piece I pull out. Okay, my question would be, well, how do I find the electric field from this continuous charge distribution? Let's pick a specific point. I'm going to go straight off the bottom edge and pick a spot over here. Okay, we'll say this is location X. So the distance from here to there is X. Alright, what's the electric field at that point from this continuous charge object? Well, the way we would do it if it was a bunch of point charges is we'd add up the individual contributions. So if I had a single charge there, and a single charge there, and a single charge there, well, I'd find the field here from this piece, and then the field there from this piece, and the field at this point from that piece. And I'd have to be careful to add their components and individually, so the X components, add them all together, the Y components, add them all together, and then I could express the electric field there. Well, if I just add a couple more charges, point charges, well, I just need to add those contributions as well. And then I could add some more charges, and I'd have to add fields for those individually. And they'd all be pointing in different directions, and I'd have to add all their X components and their Y components separately to be able to find the total electric field. Well, for a continuous charge distribution, we basically consider it to be an infinite number of small charges, okay, but we break it into little pieces. And so, for example, I could say that this is made up of a whole bunch of small chunks of charge. And so let me just pick one. Let me pick that piece right there and give it a charge of dq. Okay. Now the d in this case, it's our derivative d, or integral d. It means small, so it's not a length or something like that. This is dq. You say it together. It's a small bit of charge. Okay, a little piece of the total charge. That's what the dq means. So think about derivatives, dy dx, something like that, df dx. This is our calculus d, our small piece. Okay. Now, what I'm going to need to be able to solve this problem, I'm going to need to know, well, how much of this total charge is dq. I know L, and I know the big Q. I need to know how much of dq it is. Well, if I give it a small width here, let's call that dy. And again, that d is another calculus d, so it's a small y, just a small piece of the total length. Then I know something about the ratio of these two to the ratio of those two. Okay, I know that dq over dy must be equal to the total q over the total length. So the little bit of charge over the little bit of length should be equal to the total charge over the total length, which allows me to then write that dq is equal to q over L dy. Okay. And very often we may not know the total charge or the total length, but we might just know the charge density. In this case we call it a linear charge density because it's charge per unit length. And we very often give this a variable, lambda. Okay. Now this lambda is not a wavelength. This is a variable that we use to describe the linear charge density. So in this context, this lambda variable means charge per unit length, usually the total charge over the total length. That's how we calculate it. Okay, so now that we have that, I have this way of writing dq in terms of that length and some constants I know, the total length and the total charge. Okay, now to figure this out, well, I'm going to have to draw, I know that electric fields point, we'll just go ahead and assume this is a positive charge. So I know that the electric fields point away from positive charges, so along this line the field starts here and goes away from it. This is going to be dE. It's not the full electric field, it's just the electric field from this one small piece. So it's dE, a small bit of the total electric field. Okay. Then if I were to shift this, maybe up here, I would get another d that would point a little bit more like this. If I were to shift this lower, I'd get another d that would point somewhere like this. And in order to add up all those contributions, I need to be careful to add up the components. So let me just find the component of just this one, and then later we can try and add them up. So this has an x component, dex, and it's got a y component, dey. To be clear about those, I want to define an angle. I'm going to define this to be an angle theta, which you can see is the same as this angle here, because we have a straight line intersecting a straight line, so those opposite angles are the same value. And so I know that dex is going to be equal to de, and it's adjacent to this theta I've defined, so I'm going to put a cosine of that angle. Okay. So the next question is, well, what is DE? DE is the electric field from this little piece of charge. Well, I can plug that in. It's like a point charge. It's super small. So I'm going to have K times dq. Okay, that's how much charge is contributing to this field over the distance between that spot or the charge and where I'm measuring it is r squared, or r, and then I square it. So I'm going to give a variable here. That length there is r. And then I have to tack on this component, cosine of theta. Okay, that would be the component of this small piece of the total electric field. Alright, well, that doesn't look too convenient to add up all the pieces. I notice r is going to change as I shift this up and down. If I shift it smaller, r is going to get more horizontal and get shorter, and if I shift it up, r is going to get steeper and longer. Also, theta is going to change, and I need to know, I need to be able to express how dq is changing. Okay. Well, I've already done that. dq is equal to lambda dy. So I can express dq in terms of dy, which is a variable that I can change between 0 and L. So I can put that into dq, but I also want to figure out what r is. Well, for that one, I need to be careful to specify where my little charge is. So my dq has a width dy, but it has a position of just y. So y is not small. Y could be centimeters. Okay, y is where this small piece of charge is. Okay, and if that's the case, then this forms a triangle, a right triangle, with r being the hypotenuse and x and y being the other sides. And so that allows me to now write that out as k, change dq to lambda dy, r squared is going to be x squared plus y squared, and again cosine of theta, well, I can see that theta is relating the component to the full, but it's also relating these geometric values here. Its cosine is going to be adjacent over hypotenuse, and so if I plug that in, I'm going to have adjacent is x over a factor of r, which is x squared plus y squared square rooted. Okay. So now that I've got all those values, I can just do a little bit of simplification, which I will, doing it up here. Dex is equal to, pull out some constants out here, k and lambda, and then I'm going to have an x over, combining these, this is the same thing as x squared plus y squared square rooted, okay, for first power, and taking 2 over 2 times 1 over 2, the same thing as 3 over 2, it's cubing the square root. Okay, so I get that as my total value of dex. Okay. Oh, sorry, and I forgot my dy. I need to put my dy. I'm going to place that right there. Okay. So I have some constants. I have a function of the position of the charge, as well as the position I'm measuring it at, and then I have this little step in dy, and that is my integration variable. Now, this is in a form that I can integrate, because I can then say, okay, dy, and then change it to another, a little step dy higher, and then a little step dy higher, and do that from 0 all the way to L. So the way we can now write it is we can sum all those pieces together and get the total Ex. Notice this is not Dex, this is Ex. This is the X component of the electric field from this entire rod. We're going to obtain it by adding up all the pieces, and that's what this integral sign means. That is literally, the form of this integral sign is from the summation sign, meaning add up. We're adding up all the pieces that we found, and in this case it's going to be from y equals 0 to y equals L. We have our k lambda x over x squared plus y squared to the 3/2 dy. Okay, and that is my full form. Now technically we're done with the physics. We have used physics to clarify all of this. Now we need to step into our math world, and we need to solve this with some math. Now I can leave it to you for a calculus problem, but the solution to this form of an equation, form of an integrand, is, pulling those constants out, you're going to end up with y over x times x squared plus y squared square rooted. That is if I take the derivative of this with respect to y, I will get this. Okay? And so taking the antiderivative of that, I would get this. So this is the result of the integral of that function. Now I need to evaluate it between its limits from 0 to L, which means I plug L into this, and then subtract, and then do the same thing plugging 0 into this. But I can see when I plug 0 in for y, well, this whole thing goes to 0, so I don't need to do that second term. So then, plugging L into this, I end up with k lambda L, L for the y here, x squared plus L squared, square rooted. So make sure that's clear. And that is the x component for this entire rod in terms of things I know. My lambda is q over L, I know that one. Okay. X is where I'm measuring it at, so I choose what x is, and L is the length of the rod. Now I need to note that this is for a specific position. This is at a position that's level with the bottom of the rod, and I know that the electric field is pointing directly away from the rod, from the base of the rod horizontally or perpendicularly from the length of the rod. So this is a very specific result that I can't just apply to everything. It's an electric field, but it's not an electric field of a sphere, it's not an electric field of a disk, it's not an electric field of a ring or a curve, and it's not even an electric field for any line. It's an electric field only for this configuration of the position relative to the base of this rod. So I do have to be careful with these. Okay, we can solve for a lot of very convenient and useful configurations, but we need to recognize that each result is specific to a specific configuration. Okay. Now I can box this in, and that would be a fine result to use. But I want to take this in two directions. One, what if I am really far away from this rod? I'm crazy far away from this rod, so that x is much bigger than L. Okay, x is much bigger than L. So this rod is teeny tiny compared to how far away I'm measuring its field. Well, if that's the case, if x is much greater than L, then x squared plus L squared is basically x squared. There's not much of a difference between a million squared plus 1 squared versus a million squared. Okay, so I can just get rid of the L here. Now I can't get rid of it here, because if I say that L is much smaller than x up here, then I basically make this whole thing look like 0, which is too much of an approximation. It's a coarse approximation. But I can get rid of it here because x plus L, with L being super small compared to x, we can get rid of that, and that's a fine approximation. Okay, so in doing so, I end up with k lambda L. So now I have x squared, square rooted, times x, gives me x squared. Okay. Now that may not look special, except I do recognize that I get that characteristic 1 over distance squared that I need to have. But if I remember that lambda was a variable we used to call the charge density, but we got it from saying total charge over total length. If I replace that, I get k q over L times L over x squared. The L's cancel, and in this approximation I end up with the electric field being k q over x squared, which is the electric field of a point charge with size q, and I'm a distance x away. Now think about that. Is that the result we should get? If you think carefully, if you're staring at this rod of charge and you walk further away, the rod appears smaller. You walk even further, the rod appears smaller. There's going to be a point where you're going to walk so far away that the rod is so small you can't even tell it's a rod anymore. It just looks like a spot. Well, if that's how we see it, then our electric field ought to be measured in that same way. Okay? Because of that, this electric field looks like a point charge when I'm really far away. And so I'm going to put a check mark there. That's actually a way of verifying that my result makes sense. Okay? And so there are going to be, this is called, the limiting case, where we can actually take a limit to x is huge compared to L and see what it looks like. In other cases, it might be convenient to say x is super small compared to some dimension of the problem and see does it make sense, okay, or how useful is it. And so that's a really important use of that method. So this is a complete example of how we're going to do a continuous charge distribution. I used a rod of length L and uniform charge Q to demonstrate the process. Now, the same process can be applied to a rod of a full length, and I measure from the middle of the rod. It would give a little bit of a different result. In fact, we can start with this result. I encourage you to try that. Or we can do, maybe find the electric field below a rod along its axis. We could follow the same process. What if I have a bent rod? I could do it for that. And it's not just rods. This process applies to a disc. What if I do it for a disc, or a ring, or a sphere, or a plate? Just all sorts of different configurations. The main idea is that you have to break up the total charge, the total object, to a little piece of charge with a little dimension, whatever that convenient dimension is. And then you have to break it into components to source from that little piece. Find the electric field for that little piece in terms of an integration variable. In this case it was y, because all the charge was along y. It could be described very conveniently as its position along y. So dy was a convenient integration variable. And then we just have to integrate it to find the total component, or the component of the total electric field for the entire charge, and then we do some math. But lastly, we came back and did some more physics to think about, does it make sense in some limit that is useful.